Welcome to Science for Sleep, where we explore the wonders of science slowly, gently, and at a pace designed to help your mind unwind. Tonight, we're going to drift into one of the most mysterious and surprisingly peaceful ideas in the cosmos: what a black hole truly is. We'll also explore, calmly, softly, what it would feel like to fall into one. Not in a dramatic or frightening way, but in a slow, dreamy, physics-based way that settles the mind rather than stirs it. Before we begin, you may notice that throughout this video, the narration includes longer, softer pauses between thoughts. These are intentional. They create space for your mind to absorb the science without rushing, and they help your breathing slow into a gentler rhythm. These pauses are part of how Science for Sleep guides you toward rest, while still giving you something beautiful and thoughtful to listen to. A black hole is often portrayed as a violent monster in space, but the truth is far calmer, far quieter. A black hole is simply a region of space-time curved inward by gravity, not a hole, not a spinning drain, not a ripping force, just a smooth, deep indentation in the fabric of the universe. If space were a soft, infinite sheet stretched in all directions, a black hole would be the deepest curve, a place where the sheet folds inward so perfectly that even light follows the descent. There's nothing chaotic about it, nothing explosive, nothing noisy, just gravity shaping space-time into a perfect, quiet well. Black holes form when very massive stars reach the end of their lives. After millions of years of shining, a star eventually runs out of fuel. Its outer layers drift away, and the core slowly collapses under its own weight. This collapse is not an eruption. It is more like a long cosmic exhale, a surrender to gravity. Over time, the star becomes dense enough to curve space-time so deeply that a black hole appears, a transformation from light into geometry. If you were to hover nearby, safely from a distance, you wouldn't see chaos. You would see a perfectly smooth sphere, darker than the space around it. The darkness is not because the black hole is swallowing everything, but because light cannot escape the curvature. Light doesn't burn, tear, or scream. It simply follows the path of space-time, drifting inward and fading gently from view. The boundary around a black hole is called the event horizon, but it's not a wall or a surface. It's just the point where outward paths become inward paths. Nothing special happens there physically. No tearing, no sudden change, just a smooth crossing from one type of motion into another. And if a person were to fall in, drifting slowly, without fear, the experience would feel surreal rather than violent. Time would stretch around them like warm syrup. The universe behind them would appear to slow, while their own experience remained calm, steady, unhurried. The closer they drifted, the more space-time would lengthen beneath them, pulling them gently inward. But that part of the journey will come later tonight. Right now, imagine the black hole as a quiet, perfectly curved shape in space. No sound, no turbulence, just geometry and gravity working together with absolute stillness. A black hole is, in many ways, the universe at its most elegant, a pure expression of how space-time bends in the presence of mass. As we explore black holes together, their horizons, their time dilation, their growth, their glow, and even the soft speculation about what lies beyond them. Let yourself relax into the rhythm. There is nothing you need to remember, nothing to understand perfectly, nothing to solve. Just let the calmness of the cosmos carry you. When you're ready, we can drift into the next idea. Falling into a black hole is often portrayed as something chaotic or terrifying, but in reality, and especially when explained gently, the experience is far stranger, softer, and more peaceful than most people imagine. Tonight, we're not picturing danger or harm. We're imagining a calm, drifting descent into curved space-time itself. A slow, sensory experience where the laws of physics stretch and soften around you like a dream. If you were floating toward a black hole, the first thing you would notice is how quiet everything feels. There's no rushing wind, no sound at all, in fact. Space remains silent, as it always is. Your motion would feel smooth, unforced, almost weightless. A gentle drifting, as if being carried by a slow underwater current. From far away, the black hole looks like a perfectly dark sphere, surrounded by a faint halo of light from distant stars, whose paths bend around it. But as you drift closer, nothing sudden happens. There are no jolts, no waves, no shaking. Gravity simply guides you more firmly, like a soft slope gradually steepening beneath you. Your sense of time would begin to stretch long before your body felt anything unusual. This is because of gravitational time dilation, the way gravity slows time itself. To you, everything would feel normal, steady, continuous. But if someone were watching from a distance, your movements would appear slower and slower, as though you were sinking gently into syrup. Your gestures, your drifting, even your breathing would seem to take longer and longer. But you wouldn't feel this stretching. Your internal sense of time would remain smooth. Your heart would beat normally. Your thoughts would unfold at their usual pace. It's only the universe around you that would begin to behave differently. As you approach the event horizon, the invisible boundary where light can no longer escape, you still wouldn't feel anything dramatic. This is one of the most surprising truths about black holes. Crossing the event horizon is physically uneventful. There's no wall, no edge, no sensation, nothing at all to mark the transition. You would simply drift across a point where all outward paths now curve inward. Imagine crossing into a quiet, soft interior space, not darker, not colder, not violent, just deeper. A deeper curve in space-time, a continuation of your fall. The light from the universe behind you would begin to distort gently, stretching and shimmering as gravity bends it. The stars might appear to drift in unusual arcs. Colors may shift slightly, but all of this would feel strangely peaceful, like watching reflections ripple across water. There is a concept called spaghettification, often described in dramatic ways, but it only applies to small black holes with extremely sharp gravitational gradients. In the calm science we're exploring tonight, imagine instead a supermassive black hole, the kind found at the center of galaxies. These black holes are so large, millions of times more massive than the Sun, that their gravitational pull near the event horizon is actually gentle, far gentler than the gravity on Earth. You wouldn't feel stretched. You wouldn't feel pulled apart. You wouldn't feel anything unusual at all. Inside, the fall becomes purely geometric. You're no longer moving through space. Space itself is moving you. You drift inward the way a leaf drifts down a slow-moving river. There's no sense of speeding up, even though space-time is guiding you ever deeper. The horizon behind you disappears into a smooth darkness, and the universe begins to narrow into a soft, glowing ring of distorted light. Time becomes even stranger here. Moments within your body continue normally, yet the outside universe appears to race forward, as if someone pressed fast forward on reality. Galaxies spin, stars evolve, light drifts across the cosmos. You feel steady and slow, while everything beyond glimmers with accelerated motion. Inside the horizon, all paths curve inward. This isn't a threat. It's simply the natural shape of space-time. You're following the deepest valley of gravity's gentle landscape. If you imagine falling through a tunnel of darkness, picture it not as cold or frightening, but as serene, a quiet, luminous void where physics becomes soft and unfamiliar. Every sensation is muted, every thought is slower, every moment feels like it's drifting. You're not falling in the way we fall on Earth. You're gliding along the universe's most elegant curve. The deeper you go, the more dreamlike the experience becomes. Sight becomes abstract. Light bends in ways the mind can barely interpret. Time may feel thicker, like honey. Your awareness might float between clarity and calm, the way it does just before sleep. And here, in this impossible quietness, you're experiencing one of the most extraordinary structures in the universe. Gently, safely, from a place of imagination and rest. Black holes are often portrayed as terrifying, but tonight they are peaceful, silent, dreamlike. A reminder that even the universe's strangest places can be understood softly, without fear. When you're ready to continue, we'll drift outward for a moment and explore the calm gravity of the collapsing stars that create these beautiful curves in space-time. To understand how black holes come into existence, we return to something gentle, familiar, and deeply poetic, the quiet ending of a massive star's life. Despite how dramatic star death is often portrayed, the true process, especially when viewed across cosmic timescales, is slow, calm, and almost meditative. A star spends millions or even billions of years shining steadily, holding itself open against gravity through the warmth and pressure of nuclear fusion. It is stable, balanced, and serene, and gradually, almost imperceptibly, that balance begins to shift. A star does not simply explode into chaos to form a black hole. Instead, it exhales its energy over millennia. Its core cools, its reactions slow. Its outer layers drift and expand like a soft, glowing mist. Gravity, which had been quietly waiting, begins to play a larger role. Not violently, but patiently, steadily, with the same calmness that shapes orbits and moves galaxies. Imagine a star living out its last moments with dignity. Its light dims, its outer layers loosen. The delicate tug of war between outward pressure and inward gravity slowly tips to one side. Gravity, becomes the quieter, stronger whisper, inviting the star inward. For a massive enough star, the core collapses under its own weight. But this collapse isn't the instant disaster often depicted. If you zoom out to a cosmic perspective, the process is smooth. A gentle gathering of mass as gravity takes over more and more of the star's structure. The atoms inside lose their ability to resist compression. The star folds inward, layer by layer, until its material is compressed into an astonishingly small region. This is how the seed of a black hole is made. Gravity doesn't tear the star apart. It simply removes the pressure that once held it open, allowing the star to settle into a deeper configuration of mass and curvature. Like a heavy blanket folding onto itself, the star becomes denser, more compact, and ultimately transitions into the deepest, softest curve in space-time. From the outside, this transformation is quiet. The surrounding universe barely notices. The star blooms outward in a final release of light, a supernova. But even that can be imagined gently here. Not an explosion of violence, but a spreading of stellar petals drifting outward across space. The core, now free from its outer layers, continues its inward journey, compressing further and further until space-time curves around it completely. And then, without a sound, without a shockwave, without any visual drama, a black hole appears. A smooth, dark sphere, perfectly calm, a new geometric shape in the universe. In many ways, the black hole is simply the star's final form, a quiet remnant that no longer shines outward, but instead curves inward. Its gravity doesn't reach out to grab things. It doesn't yank or pull. It simply sits, still and silent, reshaping the flow of anything that wanders close enough. Stars orbit it peacefully. Gas drifts around it in slow spirals. Light bends gently around its edges. A star collapsing into a black hole is the universe changing shape, not falling apart. Inside that collapsed core, matter becomes so dense that its gravitational influence changes space-time in the deepest way possible. But again, nothing violent is happening in the moment. The collapse is complete. The structure is stable. The geometry is set. Once a black hole forms, it becomes one of the calmest, most unchanging objects in existence. A black hole is, in essence, gravity at rest. It no longer shines. It no longer burns. It no longer changes rapidly. It simply exists, still, stable, and timeless. When you imagine this process, try to picture the calmness instead of the drama, the slow cooling, the soft dimming, the steady collapse, and then the quiet, dark sphere left behind. A black hole begins not with chaos, but with a star drifting into its final graceful shape. And with that shape established, we can now explore one of its most important features, the strange, gentle way space-time curves so deeply around a black hole that even light cannot escape. To understand why light cannot escape a black hole, imagine space not as emptiness, but as a smooth, flexible fabric stretching gently in all directions. Every object, planets, stars, you, rests on this fabric, creating small indentations. Gravity is simply the way objects move along these curves. The bigger the mass, the deeper and smoother the indentation becomes. A black hole is the deepest curve that nature can create. Not sharp, not violent, just a perfectly smooth well in space-time. Light normally travels in straight lines, but in curved space-time, straight simply means following the bend. When space-time curves around a massive object, light bends too, gliding along the contours of the gravitational shape. Around Earth or the Sun, this bending is subtle. Around a black hole, the bending becomes so deep, so complete, that every possible path curves inward. This is why light cannot escape, not because it's trapped or stuck or grabbed, but because every path that light could take leads inward, like raindrops sliding down a smooth, perfectly shaped bowl. There is no outward route, not because something blocks it, but because an outward path simply does not exist in that region of space-time. If you imagine a photon, a tiny particle of light, drifting near a black hole, you can picture it riding along the slopes of the curved fabric. At a distance, the curve is gentle. The photon's path bends slightly, like a leaf caught in a soft breeze. As it drifts closer, the slope steepens. The light bends more noticeably, and if it crosses the event horizon, it continues drifting inward, following the deepest part of the curve. Nothing forces the light inward, nothing grabs it. It simply follows the geometry. The event horizon is the place where the curvature becomes so deep, so complete, that all paths, even the ones pointing outward, fold inward. There is no physical edge, nothing glowing or tangible, just a smooth transition from broad space-time into the deepest gravitational valley nature allows. A helpful way to visualize this is to picture yourself standing on a hillside at dusk. If the slope is gentle, a ball placed at your feet will roll slowly. If the hill becomes steeper, the ball rolls faster. And if the land suddenly descends into a vast valley, everything nearby naturally moves toward the deepest point. A black hole is that valley in space-time, a shape, not an object. But unlike a physical hill, a black hole's curve grows so steep near the horizon that even light, the fastest thing in the universe, cannot climb it. Here's something calming to remember. The curvature is not chaotic. It's perfectly smooth, like a gently drawn mathematical curve. Space-time wraps around the black hole in precise, elegant shapes. There are no jagged edges, no abrupt changes, just a continuous gradient from the shallow slopes of normal gravity into the deep well of the event horizon. When we say that light cannot escape, what we're really saying is that the geometry is closed. Paths that once led outward gradually rotate inward until they all converge toward the center. It's a cosmic one-way direction, not enforced, just shaped. If you were drifting near the event horizon, the light from distant stars behind you would bend into beautiful arcs. The universe would curve around your vision, creating a soft ring of distorted starlight. This is gravitational lensing, space-time acting as a gentle magnifying glass. It's one of the most stunning sights in astrophysics, and it arises entirely from curvature, not force. The idea that black holes pull things in is a misconception. Gravity is not a pull. It is the shape of the universe. Objects move along the shape. light moves along the shape, and near a black hole, the shape simply bends inward in a way that leaves no route back out. If you could freeze time and watch light near a black hole, you would see photons spiraling gracefully toward the horizon, riding the curves like leaves on a slow-moving current. Some would circle the black hole in almost perfect loops at a place called the photon sphere, orbiting in delicate rings of gravity before eventually drifting inward. It's all movement guided by geometry. Calm, smooth, quiet. This is the essence of why black holes are not violent monsters. They are pure curves, elegant structures shaped by mass, existing silently in the darkness. Light cannot escape, not because there is danger, but because the universe has shaped space-time so deeply that there is no outward path to take. In the next section, we will drift closer to that invisible boundary, the event horizon, the silent, smooth threshold where the curvature becomes complete. The event horizon is one of the most misunderstood ideas in all of astronomy. It's often imagined as a physical surface, a kind of cosmic edge or a glowing boundary, or even a swirling ring of danger. But the truth is much gentler and much simpler. The event horizon is not a wall. It is not a barrier. It is not something you can see, touch, or feel. It is simply the place where the direction of space-time curves entirely inward. Nothing dramatic happens there. No alarms, no tearing, no sudden shift. Just a quiet point where outward motion becomes impossible because there are no outward paths left in the geometry of space. If you were drifting toward a black hole, you wouldn't know when you cross the event horizon. There's no sensation, no visual cue, no soft vibration or change in temperature. You would simply keep floating as calmly as before, without the slightest hint that you had passed an invisible threshold. That is the quiet beauty of the event horizon. The universe changes shape around you, but you don't feel the change. Imagine walking across a border between two countries when the line is painted on the ground but nothing else is different. The grass looks the same, the air feels the same. The world continues exactly as before. Crossing the event horizon is even subtler. The line isn't painted, and nothing marks the moment. You only know it happened because every possible path now curves inward. This boundary forms because space-time has been curved so deeply by the mass of the black hole that light, even traveling at the fastest speed possible, cannot climb back out. It's not a prison. It's not a trap. It's simply the geometry of gravity taken to its quiet, elegant extreme. From the outside, the event horizon appears completely black, not because something hides behind it, but because no light returns from within. The surface looks smooth, perfectly round, and utterly silent, as if the universe has drawn the cleanest possible circle around nothingness. If starlight streaks behind it, you might see a shimmering ring of brightness called the photon sphere, where light briefly loops the black hole before drifting away. But the horizon itself remains dark and calm. The horizon silence is part of what makes black holes so peaceful when understood correctly. There's no roar, no sucking motion, no spinning vortex, unless there is nearby matter swirling, which is separate from the black hole itself. The event horizon does not pull anything in. It simply marks the point where falling inward becomes unavoidable. Inside the horizon, all movement, even movement that once felt upward or sideways, is now a direction inward. Not because you're being forced, but because the structure of space routes every possible path that way. It's like walking through a valley where every slope leads toward the center. No matter which direction you choose, every step brings you deeper. Even time behaves differently here. Your personal time feels normal, steady, unbroken. But to someone watching from far away, your fall appears to slow endlessly. From their perspective, you never quite reach the horizon. You drift closer and closer, fading into stillness. To you, however, the journey continues with no interruption, completely unaware that you've crossed the boundary in their view. This difference, the contrast between internal experience and external observation, is one of the most poetic aspects of black holes. Two truths exist at once. Two perspectives, both valid. Two different timelines unfolding together. As you drift deeper, the horizon stays behind you, invisible and silent. No sound, no glow, no trace. It simply becomes part of the background, as unremarkable as the space you passed through minutes earlier. Many people expect the event horizon to be frightening, but when understood through calm physics, it represents something far more peaceful. The smoothest possible threshold in the universe. A place where the shape of reality transitions gracefully into its deepest curve. As we move forward, we'll explore what happens to time itself as you approach and cross this boundary. How moments stretch, how the universe around you transforms, and how the passage of time becomes as fluid and dreamy as the quiet space around a black hole. Time behaves differently near a black hole, but not in a chaotic or frightening way. Instead, the change is slow, smooth, and strangely beautiful. Like watching syrup thicken or listening to a song gradually slow down without losing its melody. Near a black hole, time itself becomes gentle, stretched, softened. What feels like a normal moment to you becomes, to the rest of the universe, something that elongates gracefully. To understand this, imagine time as another dimension woven into the fabric of space. Just as gravity curves space, it curves time as well. The stronger the gravity, the deeper the curve. And the deeper the curve, the slower time flows. Not because anything is malfunctioning, but because that's how the geometry of the universe naturally behaves. If you were drifting toward a black hole, everything in your body would continue normally. Your heartbeat, your breathing, your blinking, your thoughts. You would feel no internal stretching or distortion. Your 1 second would still feel like 1 second. But from the perspective of someone watching from far away, your seconds would begin to lengthen. Your motion would slow. Your fall would appear delayed, like watching someone move through thick, warm honey. The closer you drifted to the event horizon, the more pronounced this effect would become. At first, the difference would be subtle, a slight lag, barely noticeable. But as you approach the horizon, your fall would appear to slow dramatically. From the outside, it might look as if you were hovering, frozen just above the edge, suspended in time. You would never quite be seen crossing it. But to you, nothing would feel unusual. Time would continue flowing normally, soft, steady, familiar. This is one of the most poetic aspects of black holes. Two perceptions of time coexisting. Two truths, both valid. Two timelines unfolding together, yet experienced completely differently. Far away, the universe continues at its usual speed. Stars age, galaxies rotate, light travels, events unfold. But close to the black hole, your personal experience stretches those moments into something dreamlike. You float in slow motion relative to the cosmos, caught in a graceful gradient of time dilation. This isn't slowing caused by fatigue or fear. It is purely gravitational. Time is being shaped by geometry. If you could look back toward the universe as you drifted closer to the horizon, you would see something extraordinary. The cosmos would appear to speed up. Stars might seem to move faster. Light from distant galaxies would shift in color, growing bluer as their wavelengths compress. It might look like the universe is subtly accelerating while you remain calm, drifting inward at your own pace. Inside your own experience, however, everything remains peaceful. Your thoughts feel normal. Your breathing feels normal. You sense no distortion in yourself. The stretching exists only in the relationship between you and the universe beyond. Imagine sitting beside a quiet river, watching the water slow as it approaches a bend. Upstream, the current flows steadily. At the curve, the movement becomes deeper and smoother. This is how time behaves near a black hole. Steady upstream, slow at the bend, with you drifting along the curve. Within the event horizon, the stretching becomes complete. Time flows inward, just as space does. Every possible future leads deeper into the black hole. But this doesn't feel frightening. It simply feels directed, like being carried along the deepest current of reality. Gravity does not distort your experience violently. It reshapes the pathways of space and time, and you glide along those pathways automatically, without resistance and without alarm. If you were able to speak to someone watching from far away, your messages would take longer and longer to reach them. Your voice would stretch, lower in pitch, fading gently as time dilation sent your words outward at a slower rate. Eventually, communication would become impossible, not because anything broke, but because your timelines diverge so dramatically. This divergence is peaceful, slow, a natural consequence of gravity's deepest curve. Time near a black hole is not something to fear. It is something to marvel at. It's the universe demonstrating that time is not fixed, but flexible, not rigid, but responsive, not absolute, but shaped gently by the presence of mass. As we continue tonight, we will drift deeper into the calm mysteries of black holes, exploring what lies beneath the horizon, including the singularity, which isn't a physical object, but a place where our math quietly fails to describe what we know must exist. At the very center of a black hole lies something often misunderstood, often dramatized, and often imagined in ways that make it seem frightening. But in truth, a singularity, at least as we understand it in physics, is not a thing. It is not a point, not a spike, not a needle of destruction waiting to tear anything apart. A singularity is simply the place where our math stops working, a quiet boundary in our understanding, not a violent entity in space. When scientists say singularity, what they really mean is, we don't yet know how to describe what happens here. It is a mark of limited comprehension, not a mark of danger. If you were drifting inside a black hole, imagining this in the soft, dreamlike tone of tonight's video, the singularity would not look like anything at all. You wouldn't see a glowing point. You wouldn't feel yourself approaching anything physical. You wouldn't sense a center or a spike or a surface. You would simply continue falling inward along the geometry of space-time, with no visible destination. Nothing in your direct experience would announce, this is the singularity. Because the singularity is not part of your experience, it's part of our equations. General relativity, the theory that describes gravity as curved space-time, predicts that a black hole's center compresses matter into an unimaginably small region. But quantum mechanics, the theory that governs the very small, disagrees. The two mathematical worlds collide, and instead of giving us a clear answer, the numbers produce infinities. Places where the math spirals out of control. Those infinities are what we call singularities. But infinities do not exist in nature in the way equations suggest. Nothing in the universe is infinite in the literal sense. Everything is finite, measurable, grounded in physical reality. So when our equations give us infinite density or infinite curvature, that's not a description of the universe. It's a description of the limits of our current models. A singularity is where our scientific understanding becomes blurry, not where reality becomes violent. If you imagine drifting deeper into a black hole, all you would continue to feel is space-time curving inward. No impact, no collision, no sudden shift. Just a continuation of the same falling sensation that began outside the event horizon. In this gentle visualization, the singularity is more like a horizon of knowledge, the inner edge of what our current physics can describe. Beyond that, we need a new theory, one that unifies gravity and quantum mechanics into a single framework. Physicists call this the quest for quantum gravity, a theory we do not yet have, but one that will eventually rewrite how we understand black hole interiors. Some theories propose that the singularity is not a point, but a bounce, where space contracts and then re-expands. Others speculate that the singularity is replaced by a finite, ultra-dense core, a region where quantum pressure prevents infinite collapse. Others imagine the singularity as a smooth transition into another region of space-time. But these are speculations, gentle, imaginative possibilities, not certainties. In your quiet drifting fall, none of this would be felt. Physics happens around you, shaping your path, but it does not announce itself. There is no moment where geometry becomes sharp or dangerous. Space-time simply guides you inward until you reach the limit of what our equations can currently map. The singularity is not the end of your experience. It is the end of our scientific language. And yet, this is also where the beauty lies. Because singularities remind us that the universe still holds mysteries far deeper than our current understanding. They point to realms of physics that remain undiscovered. They invite curiosity rather than fear, wonder rather than dread. In this way, a singularity is not frightening, It is profoundly peaceful. It is the quiet reminder that some parts of the cosmos remain hidden, waiting for future science to illuminate them. As we continue, we'll drift away from the center and explore how black holes grow, not through violence, but through slow, silent accumulation that shapes the structure of galaxies. At the very center of a black hole lies something often misunderstood, often dramatized, and often imagined in ways that make it seem frightening. But in truth, a singularity, at least as we understand it in physics, is not a thing. It is not a point, not a spike, not a needle of destruction waiting to tear anything apart. A singularity is simply the place where our math stops working, a quiet boundary in our understanding, not a violent entity in space. When scientists say singularity, what they really mean is, we don't yet know how to describe what happens here. It is a mark of limited comprehension, not a mark of danger. If you were drifting inside a black hole, imagining this in the soft, dreamlike tone of tonight's video, the singularity would not look like anything at all. You wouldn't see a glowing point. You wouldn't feel yourself approaching anything physical. You wouldn't sense a center or a spike or a surface. You would simply continue falling inward along the geometry of space-time with no visible destination. Nothing in your direct experience would announce, this is the singularity. Because the singularity is not part of your experience, it's part of our equations. General relativity, the theory that describes gravity as curved space-time, predicts that a black hole's center compresses matter into an unimaginably small region. But quantum mechanics, the theory that governs the very small, disagrees. The two mathematical worlds collide, and instead of giving us a clear answer, the numbers produce infinities, places where the math spirals out of control. Those infinities are what we call singularities. But infinities do not exist in nature in the way equations suggest. Nothing in the universe is infinite in the literal sense. Everything is finite, measurable, grounded in physical reality. So when our equations give us infinite density or infinite curvature, that's not a description of the universe. It's a description of the limits of our current models. A singularity is where our scientific understanding becomes blurry, not where reality becomes violent. If you imagine drifting deeper into a black hole, all you would continue to feel is space-time curving inward. No impact, no collision, no sudden shift. Just a continuation of the same falling sensation that began outside the event horizon. In this gentle visualization, the singularity is more like a horizon of knowledge, the inner edge of what our current physics can describe. Beyond that, we need a new theory, one that unifies gravity and quantum mechanics into a single framework. Physicists call this the quest for quantum gravity, a theory we do not yet have, but one that will eventually rewrite how we understand black hole interiors. Some theories propose that the singularity is not a point, but a bounce, where space contracts and then re-expands. Others speculate that the singularity is replaced by a finite, ultra-dense core, a region where quantum pressure prevents infinite collapse. Others imagine the singularity as a smooth transition into another region of space-time, But these are speculations, gentle, imaginative possibilities, not certainties. In your quiet drifting fall, none of this would be felt. Physics happens around you, shaping your path, but it does not announce itself. There is no moment where geometry becomes sharp or dangerous. Space-time simply guides you inward until you reach the limit of what our equations can currently map. The singularity is not the end of your experience. It is the end of our scientific language. And yet, this is also where the beauty lies. Because singularities remind us that the universe still holds mysteries far deeper than our current understanding. They point to realms of physics that remain undiscovered. They invite curiosity rather than fear, wonder rather than dread. In this way, a singularity is not frightening. It is profoundly peaceful. It is the quiet reminder that some parts of the cosmos remain hidden, waiting for future science to illuminate them. As we continue, we'll drift away from the center and explore how black holes grow, not through violence, but through slow, silent accumulation that shapes the structure of galaxies. One of the most surprising and visually stunning things associated with black holes isn't darkness, it's light. Brilliant, towering jets of light and energy can stream outward from regions around some black holes, stretching for thousands or even millions of light years. These jets look intense and powerful in images, yet their origin is gentle, orderly, and entirely outside the black hole itself. They are not explosions. They are not eruptions. They are not the black hole spitting anything out. They are the universe's way of threading light through magnetic fields near the event horizon, guiding it outward with remarkable smoothness. To understand these jets, imagine the accretion disk from the last section, the glowing ring of gas and dust that orbits just outside the event horizon. This disk spins, and as it spins, it drags magnetic fields with it, winding them tighter and tighter, like soft ribbons twisting around a pole. As these magnetic fields become more organized, they form two narrow, elegant channels aligned with the black hole's rotation. These channels are the pathways through which particles and light escape. The jets do not come from inside the black hole. Nothing escapes from beyond the event horizon. Instead, the jets form just outside the horizon, where matter is still free to move outward. Here, magnetic fields gently redirect energy upward and downward, away from the disk and into straight, narrow beams. Imagine sunlight filtered through a crystal, forming a precise beam of brilliance. The jets are that idea on a cosmic scale. Although the jets look fierce in photographs, especially in enhanced colors, their formation is smooth and controlled, an expression of the orderly physics surrounding a spinning black hole. The magnetic field lines guide the motion like rails, shaping the flow into long, thin streams that travel at speeds close to light. If you were floating far away, watching one of these jets, it would appear almost like a candle flame in slow motion, unwavering, narrow, and astonishingly straight. Not chaotic, not explosive, just constant, patient emission of light and particles. Some jets extend farther than the diameter of entire galaxies. They illuminate surrounding gas, carve structures into intergalactic space, and sometimes seed regions where new stars form. They are engines of energy, created not by violence, but by the quiet, persistent rotation of space-time. It's important to emphasize that the black hole itself is not producing light. The hole remains perfectly dark. The glow and the jets come entirely from the matter orbiting just outside the event horizon. Matter heats up as it swirls, and magnetic fields funnel some of that energy outward. The black hole is simply the anchor around which this dance happens. If you could drift near the region where jets form, still at a safe, imagined distance, you'd see an extraordinary ballet of physics. The accretion disk would glow softly, like a warm ring of light. The jets would shimmer as thin, luminous columns, rising straight upward and downward. Space around them would distort gently, with starlight bending like warm glass. The motion would be smooth, unhurried, and mesmerizing. In real galaxies, these jets can even influence the shape and behavior of galaxy clusters. They stir gas on enormous scales, helping regulate temperature and star formation. This is not destruction. It is gentle cosmic engineering, carried out by streams of light and energy traveling through vast distances. All of this happens while the black hole itself remains silent and still. The jets remind us that black holes are not dead regions of space. They are dynamic hubs of physics, not because they erupt, but because the environment around them becomes a beautifully organized structure. Space-time curves inward, magnetic fields twist, plasma spirals gracefully, and light finds its path outward. It is one of the most serene contradictions in the universe, that the darkest objects can produce some of the brightest structures. As we continue, we'll step back and look at the largest members of this cosmic family, the supermassive black holes that sit quietly at the hearts of galaxies, shaping them slowly over billions of years. Supermassive black holes are some of the most extraordinary structures in the universe, not because they are dangerous or chaotic, but because of their sheer scale, stability, and calm presence. These giants sit at the centers of nearly every large galaxy, including our own Milky Way. They are millions, sometimes billions of times more massive than the Sun. And yet, despite their size, they are among the quietest objects in existence. To imagine a supermassive black hole, picture a dark sphere so large that it could fit our entire solar system inside its horizon. But size doesn't translate to violence. Quite the opposite. The larger a black hole is, the gentler its gravitational gradient becomes near the horizon. If you drifted toward a supermassive black hole, especially one with no nearby accretion disk, the experience would feel calm, almost uneventful. These black holes form differently from their smaller cousins. Stellar black holes come from collapsing stars, but supermassive black holes grow over billions of years through a slow combination of processes, merging with other black holes, absorbing drifting gas, and collecting the quiet remnants of stars that wander too near. Their growth is not sudden, not explosive, just the soft, patient accumulation that defines cosmic time. What makes supermassive black holes special is not just their mass, but their influence. They act as the anchor points of galaxies. Their gravity helps shape the motions of stars. They stabilize galactic centers. They guide the orbits of surrounding material, not by pulling everything inward, but by creating a deep steady well in space-time that galaxies naturally settle around. Imagine placing a heavy stone in the middle of a large pond. The water doesn't rush toward it. It simply curves around it, forming gentle patterns and orbits. This is how stars behave near a supermassive black hole. They orbit peacefully, tracing elegant loops through space, rarely coming close enough to be captured. In galaxies with active accretion disks, supermassive black holes can be surrounded by glowing rings of gas, warm spirals that shine as particles rub together on their way inward. But in many galaxies, including our own, the central black hole is quiet. There is very little nearby gas. There is no raging brightness. There are no dramatic jets. Sagittarius A, the Milky Way's central black hole, shines only faintly in radio wavelengths and otherwise sits in darkness, serene. If you were to drift near a supermassive black hole, imagining this safely and calmly, the experience would be surprisingly peaceful. Space would appear slightly distorted. Light from stars behind it would bend into arcs. The horizon itself would look perfectly smooth, like a dark glass sphere floating in the void. Its size would make the descent even more surreal. Unlike smaller black holes, which create sharp gravitational gradients near the horizon, supermassive black holes have extremely gentle curvature across enormous distances. You could cross the event horizon without feeling any difference at all. Your body wouldn't stretch. Your senses wouldn't detect any shift. It would be the quietest boundary crossing imaginable. These giants are also long-lived. A stellar black hole slowly evaporates through Hawking radiation over unimaginable spans of time. But a supermassive black hole evaporates even more slowly, so slowly that the universe itself is not old enough for a single one to have noticeably changed. They are, in many ways, the most stable things the cosmos has ever created. Supermassive black holes also play a role in galactic evolution. Their jets, when present, can regulate star formation by stirring surrounding gas. Their gravity influences the distribution of stars. Their presence helps define the heart of a galaxy. And yet, they do all of this without sound, without motion, without forceful interaction. They shape the cosmos by simply existing, by being the deepest curve in the space-time around them. When we think of black holes, it's easy to imagine chaos. But these enormous structures embody the opposite. They are quiet order, cosmic architecture, the still centers around which galaxies dance. Next, we'll narrow our focus and look at the black hole closest to home, Sagittarius A, the gentle giant at the heart of the Milky Way, sitting in darkness and silence, just 26,000 light-years away. At the heart of our Milky Way galaxy, in a region filled with drifting stars, glowing dust, and soft ribbons of gas, sits a black hole unlike any other we've explored tonight. Its name is Sagittarius A, a calm, steady giant resting in the center of our galaxy, shaping the motion of stars with quiet, constant gravity. Sagittarius A is a supermassive black hole, but not an active or chaotic one. It isn't surrounded by a brilliant accretion disk. It doesn't release enormous jets. It doesn't dominate its surroundings through violent eruptions. Instead, It sits in a peaceful corner of space, influencing its environment through gravity alone. We know it exists not because we see it, but because we see the motion of stars around it. Astronomers watch tiny, bright stars near the galactic center, completing elegant orbits around something invisible, something enormously massive, yet perfectly dark. These stars move so quickly, tracing loops that take only a few years to complete, that nothing except a supermassive black hole could explain their motion. If you could drift above Sagittarius A, the view would feel serene. You would see stars floating through the darkness in graceful arcs, orbiting smoothly as if choreographed. Some would move slowly. Some would whip around the center at incredible speeds. But none would look chaotic. They follow the same gentle rules of gravity that guide planets around the sun. The black hole itself would appear as a silent, round shadow against a backdrop of stars. No glow, no radiation, no visible activity, just a perfectly dark silhouette shaped by the absence of escaping light. Sagittarius A is unusually quiet for a black hole of its size. It feeds very little. There is almost no gas nearby for it to draw inward. Most of the time, it simply rests, a massive, unmoving presence at the center of the galaxy. This stillness is one of the things that made imaging it so difficult. In 2022, the Event Horizon Telescope collaboration released the first picture of Sagittarius A. What we saw was a soft, hazy ring of warm light surrounding a dark center. The ring is the glow of gas drifting near the event horizon, illuminated by the bending of space-time itself. The image looks fuzzy and dreamlike because the environment around Sagittarius A is faint, calm, and constantly shifting over the hours it takes to gather enough light. If you could float nearby, you would feel none of the drama people associate with black holes. You would see gentle distortions in starlight, forming arcs and shimmering halos caused by gravitational lensing. You might watch a cloud of dust drift lazily around the region, glowing softly in scattered light. Everything would unfold slowly, patiently, without urgency. Sagittarius A acts as the anchor point of the Milky Way. Its mass stabilizes the central region. Its gravity guides the orbits of millions of stars. Its presence shapes the core of our galaxy, the way a smooth stone shapes the patterns of water flowing around it. And despite its unimaginable size, Sagittarius A remains one of the calmest objects in all of space, a silent center, a steady gravitational heart, a dark sphere around which the galaxy gently turns. As we continue, we'll look at the remarkable effort required to capture the first image of a black hole, a process that involved telescopes across the globe working together like a single Earth-sized camera, collecting light that had been traveling across the galaxy for 26,000 years. Capturing an image of a black hole sounds impossible at first. After all, a black hole itself emits no light. Its event horizon is perfectly dark. Its interior is hidden forever from view. And yet, in 2019, humanity saw the first image ever taken of a black hole, a soft, glowing ring surrounding a dark center. Then, in 2022, we saw the same for the black hole at the center of our own galaxy, Sagittarius A. These images weren't photographs taken in any traditional sense. They were the result of extraordinary patience, worldwide collaboration, and a technique that allowed Earth itself to become a single, enormous telescope. To understand how this was done, imagine trying to capture the outline of something that gives off almost no light, from millions or billions of times farther away than any object you have ever tried to see. The black hole at the center of the galaxy, M87, whose image was released first, is 55 million light-years away. Yet from here on Earth, its event horizon appears about as large as a donut would appear on the Moon. Something that small cannot be resolved by a normal telescope. Even the most powerful individual telescopes on Earth are nowhere near large enough. So astronomers turned the entire planet into one seamless instrument. The technique they used is called Very Long Baseline Interferometry, or VLBI. Instead of using one telescope, VLBI uses many telescopes spread across Earth. In Chile, Hawaii, Spain, Mexico, Antarctica, and other locations, all observing the same object at the exact same time. Each telescope captures tiny pieces of radio waves emitted by hot gas near the event horizon, and those signals are combined using atomic clocks with precision so exact that they measure time down to billionths of a second. When all these telescopes observe together, the distance between them, thousands of kilometers, acts like the diameter of a single gigantic telescope. A telescope the size of Earth. This is what makes it possible to resolve something as small and distant as a black hole's shadow. But even then, the process is slow and delicate. Light near a black hole flickers because the gas moves and glows in constantly shifting patterns. The atmosphere above each telescope changes with weather. The telescopes themselves can only observe when the relevant part of the sky is visible in darkness. And all the observations must occur simultaneously. If even one station is cloudy or offline, data from the entire global network can be affected. For the image of Sagittarius A, the challenge was even greater. Our Milky Way's central black hole is much closer than the M87 black hole, but it is also much smaller, and it changes on short timescales. Gas swirling around it shifts rapidly, glowing differently from 1 hour to the next, while M87's black hole is extremely stable and changes slowly. Sagittarius A flickers, brightens, dims, and reconfigures within minutes. Imagine trying to take a long exposure photograph of a candle flame in the wind. The Event Horizon Telescope team had to collect many hours of data, then carefully reconstruct the average structure of the emission near the event horizon. The result? A soft ring of light surrounding a dark interior, shows the shadow of the black hole. Not the object itself, but the imprint of its curved space-time on the glowing gas around it. The ring looks blurred and hazy, almost like a glowing watercolor. This is not a flaw. It reflects the true nature of the environment. The gas near Sagittarius A is faint and constantly shifting. The Earth's atmosphere blurs radio waves, and the reconstruction process must stitch together signals from telescopes across the world, aligning them with exquisite precision. The final image is not a literal photo, but a carefully crafted map of light that has traveled for tens of thousands of years, bending around the edge of space-time before reaching Earth. Every pixel in that image represents the combined work of hundreds of scientists, thousands of hours of observation, and computational algorithms that transform scattered radio signals into a coherent picture. If you imagine floating near the galactic center while this data was being collected, you would see nothing unusual, just drifting stars and clouds of gas, illuminated by faint starlight. But the telescopes, quietly listening in radio wavelengths, would be gathering whispers of emission from the edge of the event horizon, building a picture of something perfectly dark by observing the gentle ring of light around it. It's one of the most peaceful achievements in astronomy, a global collaboration, patiently waiting for Earth to rotate, for telescopes to align, for signals to arrive, and for computers to slowly weave those signals into the first ever image of a place where light itself cannot escape. These images remind us that black holes are not just theoretical ideas. They are real structures quietly shaping the universe. And our ability to see them, even dimly, is a testament to how far human patience and curiosity can reach. When two black holes drift close enough to one another, something extraordinary begins to unfold. Not violently, not chaotically, but with a kind of cosmic patience that mirrors the quiet movements of tides or the slow drifting of clouds. Their orbits tighten over time. Their paths curve inward, and eventually they merge into one. But this process, despite the enormous masses involved, is far calmer than most people imagine. It is one of the most seamless events in the universe, guided entirely by the gentle flow of gravity and the geometry of space-time. Picture two black holes orbiting each other in the dark. They might have been born separately from different stars, or they might have drifted together gradually inside a dense region of a galaxy. For millions or even billions of years, they trace slow, spiraling paths, each black hole curving space-time around itself, and both together shaping a larger, shared gravitational landscape. The closer they get, the more they influence each other. Their orbits become tighter and more circular. They revolve like two dancers moving in perfect synchrony, neither touching the other, yet each shaping the movement of both. As they orbit, they emit something subtle: gravitational waves, tiny ripples in the fabric of space-time. These waves are unimaginably gentle. By the time they reach Earth, they stretch and compress space by less than the width of a proton. And yet, with the incredible sensitivity of instruments like LIGO and Virgo, humanity has detected these ripples, hearing the final orbital moments of distant black hole mergers as faint, ghostly vibrations. But the moment of merging, the moment people often imagine as a catastrophic collision, is not violent at all. Black holes do not crash, they do not explode, they do not burst. Instead, their event horizons blend. The smooth surfaces of space-time simply reshape into one deeper, larger curve. It is the calmest kind of union imaginable. Two geometries becoming one. From far away, if you were watching with some hypothetical, perfectly quiet vantage point, you would see the orbits accelerate as they come close. A graceful quickening, like the final rotations of dancers completing a slow waltz. Then, In the last milliseconds, their horizons touch and merge into a single, larger black hole. No shockwave, no flash, just a silent change in shape. The gravitational waves produced in these moments travel outward, soft ripples radiating across the universe, carrying with them a record of the dance. These waves are not bursts of energy in the explosive sense. They are gentle undulations, tiny changes in space-time's curvature, spreading outward like the faint rings that expand across a still pond after a single quiet drop of water falls in. The final black hole that forms is incredibly stable. It vibrates for a moment, like a struck bell settling into silence, then becomes perfectly calm. Its mass is slightly less than the total of the two black holes that merged. A small portion of the mass was converted into gravitational waves. Not light, not sound, but pure geometry rippling through the universe. If you could drift near a black hole merger, imagining this safely and calmly, you would see no chaos, no flashes, no collisions, just deep space-time curvature shifting into a new form. The jets and disks that sometimes surround black holes are external phenomena. The merger itself occurs quietly, hidden beneath the veil of perfect darkness. The ripples that reach Earth may have been traveling for billions of years. They pass through planets, stars, and galaxies without resistance. Space-time flexes gently as they move through, adjusting by a tiny amount and then returning to stillness. They carry the memory of events that occurred before humanity existed, perhaps before Earth existed. Silent messages encoded in the curvature of reality. These mergers help black holes grow. They help shape galaxy centers. They recycle mass and energy into the structure of the cosmos. And through gravitational waves, they give us a new way to observe the universe. Not through light, but through vibrations in space-time itself. There is something deeply peaceful in that idea. The universe is not only made of light and matter. It is made of gentle rhythm, soft waves that carry stories across unimaginable distances. As we continue, we'll explore another delicate possibility, the idea that some black holes may not have formed from stars at all, but from the earliest moments of the universe. Tiny black holes born in the quiet, hot fog right after the Big Bang, long before stars existed, before galaxies spiraled into shape, before even atoms had time to form. The universe was a warm, dense sea of energy. It was smooth in some places, slightly lumpy in others. Tiny fluctuations in density rippling through a hot, expanding cosmos. In those early moments, the universe was quiet in its own way, filled with soft radiation and drifting fields. And in that smoothness, there may have been places where gravity briefly gathered enough energy to form incredibly small black holes. These hypothetical objects are called primordial black holes. And though we have not confirmed their existence, the idea behind them is elegant and surprisingly calming. Instead of being born from the collapse of massive stars, primordial black holes would have emerged from the gentle imperfections in the fabric of the newborn universe. Imagine a vast, expanding cloud, perfectly uniform except for a few tiny spots where the density happened to be slightly higher. In those rare pockets, gravity could have taken hold early, not violently, but simply as a consequence of the initial conditions, pulling everything inward and forming a tiny black hole. Some primordial black holes might have been as small as mountains in mass, but only the size of atoms. Others could have been microscopic, evaporating quickly through Hawking radiation, and some, if they formed just right, might still be drifting quietly through the universe today, invisible except for their gravitational pull. The idea is peaceful. Black holes forming naturally as the universe breathes into existence. These small black holes, if they exist, would be incredibly quiet. They would not grow. They would not emit jets. They would not glow with accretion disks. They would simply drift, tiny, dense remnants of the early cosmos, operating almost like seeds of gravity sprinkled throughout space. Physicists have wondered whether these primordial black holes might even help explain dark matter, the mysterious substance that shapes galaxies but emits no light. If enough of these tiny black holes formed in the early universe, they could account for some or all of the unseen mass that helps hold galaxies together. This idea isn't proven, but it fits beautifully with the theme of cosmic calmness. Dark matter quietly guides galaxies without interacting or shining. Primordial black holes, if they exist, would do the same, drifting silently, shaping the universe without revealing themselves. You could imagine billions of these tiny black holes moving gently through the vast spaces between the stars, each one a relic from a time when the universe was only seconds old. They wouldn't disturb planets or stars. They wouldn't cause dramatic events. They would simply pass through space unnoticed, like small, dense points of gravity moving with the flow of cosmic expansion. Even the speculative nature of primordial black holes is soothing. It reminds us that the universe may hold structures we haven't yet detected, simply because they are so quiet and subtle. Not everything in astronomy is bright or dramatic. Some of the universe's most interesting ideas are invisible, calm, and theoretical. Possibilities resting gently on the edges of our understanding. If primordial black holes did form, they would be among the oldest objects in existence, older than galaxies, older than stars, older than the cosmic microwave background. Their existence would stretch back to the very beginning, connecting us to the universe's earliest moments with a quiet thread of gravity. And even if they do not exist, the concept hints at the universe's creativity. Black holes may not only be the remnants of dying stars, they might also be artifacts of the universe's birth. This possibility adds another layer to our understanding of black holes. They can begin in fire, or in silence, in explosions, or in subtle fluctuations, in the collapse of massive stars, or in the gentle unevenness of the early cosmos. As we drift forward, we'll move from the speculative to the structural, exploring how black holes, large and small, help shape the galaxies that surround them. Galaxies are enormous, sprawling structures filled with stars, gas, dust, and dark matter, all slowly rotating and evolving over billions of years. And at the center of almost every large galaxy sits a supermassive black hole, calm, dark, and immeasurably dense. While these black holes are small compared to the size of the galaxies around them, they play a subtle but profound role in shaping how galaxies grow, move, and change over time. This influence doesn't come from constant feeding or dramatic activity. It comes from gravity, the quiet architect of the universe. A galaxy begins with clouds of gas collapsing under gravity, forming stars that group together into clusters and spirals. As these early structures merge and grow, their central regions become denser. Over time, the densest parts collapse into black holes. These central black holes then serve as stabilizing anchors, shaping the way stars orbit and how the inner regions of the galaxy evolve. Imagine placing a smooth, heavy stone at the center of a shallow pond. The water settles around it. Patterns form naturally as the water flows. This is what a supermassive black hole does, not by pulling everything in, but by settling the gravitational center and defining the geometry of the inner galaxy. Even now, billions of years later, many stars deep within galaxies orbit in smooth, stable loops because of the presence of these black holes. They guide motion the way a conductor guides an orchestra, not by touching every instrument, but by setting the rhythm for the entire ensemble. Black holes also influence galaxy evolution in indirect ways. When a black hole is actively feeding, when material spirals inward through an accretion disk, the surrounding environment can glow incredibly brightly, forming what astronomers call an active galactic nucleus, or AGN. These luminous centers can outshine an entire galaxy, but their brightness isn't a sign of violence. It's light coming from gas, gently heating as it drifts inward. The energy released by this process can create soft winds that push gas outward. These winds can slow or regulate star formation, preventing galaxies from forming new stars too quickly and exhausting their gas supply early. The result is a more balanced, long-term evolution. But even in galaxies where the central black hole is quiet, which is most galaxies, its presence helps maintain order. It keeps the central region stable. It guides the motion of millions of stars. It anchors the galaxy across cosmic time. In some galaxies, pairs of supermassive black holes exist because two galaxies merged long ago. These pairs orbit one another, drifting closer over millions of years until they eventually become one. Their slow dance gently stirs the central region, redistributing stars and gas as the galaxy settles into its new shape. Even dark matter, the invisible substance that dominates the mass of most galaxies, interacts with black holes through gravity. Black holes do not pull dark matter inward in any significant way, but they influence the overall structure of the galaxy that dark matter helps support. This balance between stars, gas, black holes, and dark matter is what creates the graceful spirals, glowing halos, and elliptical shapes we see across the universe. Black holes are part of that balance, shaping galaxies not with dramatic force, but with quiet consistency. If you could drift through a galaxy, watching the movement of stars, you would see harmony. Stars orbiting in smooth curves, gas drifting in spirals, clusters of stars slowly rising and falling like waves, and at the center, often unseen yet always present, a supermassive black hole guiding the dance. The idea that such an immense and powerful object can exert its influence so calmly is one of the most beautiful paradoxes in astronomy. Black holes do not need to shine or roar to sculpt the cosmos. They shape galaxies simply by existing, by curving space-time in ways that guide everything around them. As we continue deeper into the calm mysteries of black holes, we'll explore a phenomenon almost as surprising as their mass: the idea that black holes can slowly evaporate, releasing energy in a way that transforms them over unimaginable stretches of time. Black holes are often described as eternal, unchanging objects, dark spheres that exist forever in the fabric of space-time. But in the mid-1970s, Stephen Hawking discovered something astonishing. Black holes can slowly evaporate. Not quickly, not visibly, not in any way that resembles fading or dissolving. Instead, they release a faint, delicate form of radiation that causes them to lose mass over time. This process is called Hawking radiation, and it unfolds on timescales so long that they almost defy comprehension. To understand Hawking radiation, imagine the empty space around a black hole as not truly empty. In quantum physics, even the vacuum is alive with tiny fluctuations, particles and antiparticles momentarily appearing and disappearing. These pairs normally annihilate instantly, leaving no trace. But near a black hole's event horizon, the intense curvature of space-time can separate the pair before they recombine. One particle falls inward, the other escapes outward. The particle that escapes becomes what we observe as Hawking radiation. This isn't light or heat coming from inside the black hole. It's a delicate quantum effect happening just outside the event horizon, a whisper of energy created by the geometry of space-time. As particles escape, the black hole loses a tiny bit of mass. Over immense stretches of time, it slowly shrinks. But the key is slowly. For a black hole the mass of our Sun, the evaporation time due to Hawking radiation is on the order of 10 to the 67th power years. That's 1,000,000 billion years. A span so vast that even comparing it to the current age of the universe, just 13.8 billion years, feels meaningless. If the entire universe's timeline were compressed into a single year, Hawking radiation would be something that happens in the soft, faint whispers of December trillions of times over. Supermassive black holes evaporate even more slowly, far, far longer than the universe has existed so far. They are, for all practical human timescales, eternal. Their lifetimes stretch so deeply into the cosmic future that stars may burn out, galaxies may fade, and the universe may cool into darkness long before any significant evaporation begins. And yet, the idea that black holes can evaporate at all is profoundly peaceful. It means they are not ultimate endpoints. They are not dead ends in the universe. They evolve, slowly, gently, almost imperceptibly. They release energy back into space. If you could drift near a black hole that was evaporating, imagining this in a calm, cinematic way, you wouldn't notice anything. The Hawking radiation would be unimaginably faint. Space would remain silent. The black hole surface would look dark and unchanged. Time would pass without any hint that anything was leaving the black hole at all. the evaporation is not a process you could watch. It is something that happens only when viewed from a perspective spanning unimaginable epochs. It is a phenomenon that belongs to the deep future, to an era when stars have long since faded and the universe has settled into cold quiet. Hawking radiation also connects black holes to something even more mysterious. The idea that information, the fundamental details about matter and energy, might not be lost forever inside a black hole. The radiation carries clues about quantum processes, suggesting that the universe may preserve information in ways we still don't fully understand. This idea, known as the information paradox, is one of the most important puzzles in modern physics. It challenges our understanding of quantum mechanics and gravity. It inspires new theories about the fabric of the universe, and it suggests that black holes, despite their simplicity, hold some of the deepest answers in science. The beauty of Hawking radiation is its gentleness. It's not a dramatic beam of energy. It's not a sudden collapse. It's not a cosmic explosion. It is the universe exhaling slowly through the edges of space-time. And over trillions upon trillions of years, those tiny breaths may eventually cause black holes to shrink, fade, and return their mass to the quiet background of the cosmos. In the next part of our journey, we'll explore the ideas surrounding black hole information, how the universe handles memory, what might be preserved, and why a black hole may be far more than a simple region of darkness. Black holes are often imagined as regions where everything disappears. Matter, light, energy, even the details of what once fell inside. For decades, scientists believed that once something crossed the event horizon, all information about it was erased from the universe forever. A star, a planet, a cloud of gas, all would be reduced to mass, charge, and spin, with no trace of their original identity. But quantum mechanics suggests something different. In the quantum world, information cannot simply vanish. The universe, at its deepest level, keeps track of everything. This conflict between gravity and quantum physics led to one of the greatest puzzles in science, the black hole information paradox. It's not a paradox about destruction or danger. It's a paradox about bookkeeping, about memory, about how the universe preserves the details of its own story. To understand why this paradox exists, imagine throwing a book into a fire. The pages burn, the ink curls and evaporates. The cover turns to ash. But in principle, the information in the book, the arrangement of molecules, the patterns of ink, the structure of the paper, still exists in the complex motions of smoke, ash, light, and heat. Nothing is lost completely. It simply spreads out in ways that are difficult to reconstruct. For black holes, the question becomes, if something falls in and the event horizon hides it forever, where does the information go? The laws of quantum mechanics insist that the information must persist. Yet for many years, general relativity seemed to say the opposite, that the information is gone forever behind the horizon, inaccessible and erased. Stephen Hawking once argued that information truly disappears inside a black hole. Later, he changed his mind, proposing that the information is encoded in subtle ways in the radiation black holes emit as they evaporate. Other physicists suggested that the information might be stored at the event horizon itself, in a kind of cosmic hologram. This idea, known as the holographic principle, proposes that everything inside a region of space may be encoded on its surface. In this view, the interior of a black hole, with all the complexity of the matter inside, could be encoded in a faint pattern on the horizon. Nothing is lost. Everything is preserved, just written in a form we don't yet know how to read. Some theories go even further. They propose that the quantum structure of space-time at the horizon is not smooth, but subtly textured. Not rough or jagged, but delicately patterned at scales far smaller than atoms. These patterns might store the details of everything that has fallen into the black hole across its entire history. Other ideas explore the possibility that black holes are not purely classical objects at all, but quantum systems with internal states, like atoms with many energy levels. The radiation they emit could depend on these states, carrying faint traces of the black hole's history into the universe. The truth is, we don't yet know the full answer, but the possibilities are beautiful. They suggest that the universe may be far more interconnected and far more careful with its information than we once believed. If you were drifting near a black hole, imagining this gently in the quiet of tonight's story, you wouldn't see anything resembling memory or information storage. You would simply see the dark horizon, perfectly smooth and silent. Yet beneath that silence, physics may be encoding the history of stars, planets, and particles in ways we cannot yet perceive. This idea reframes black holes entirely. Instead of being objects that destroy information, they may be repositories of it, dense, gravitational libraries, storing the quantum details of everything that has ever passed through their horizons. Not in a way people can access, not in a way we can observe, but in a way that preserves consistency in the deepest laws of nature. Physics often advances by confronting paradoxes, and the information paradox has sparked decades of progress in our understanding of gravity, quantum mechanics, and the structure of space-time. It has inspired new models of the universe that blend the smooth geometry of relativity with the discrete probabilities of quantum theory. The peaceful message behind all this is simple. The universe keeps its memories. Even in places where nothing seems to escape, something remains, encoded, preserved, waiting for a deeper understanding. As we drift into the next part of our journey, we'll explore some of the gentlest and most imaginative ideas about what might lie beyond the event horizon. Wormholes, white holes, and the possibility that space-time itself may be richer and more interconnected than we ever expected. Black holes are often imagined as regions where everything disappears. Matter, light, energy, even the details of what once fell inside. For decades, scientists believed that once something crossed the event horizon, all information about it was erased from the universe forever. A star, a planet, a cloud of gas, all would be reduced to mass, charge, and spin, with no trace of their original identity. But quantum mechanics suggests something different. In the quantum world, information cannot simply vanish. The universe, at its deepest level, keeps track of everything. This conflict between gravity and quantum physics led to one of the greatest puzzles in science, the black hole information paradox. It's not a paradox about destruction or danger. It's a paradox about bookkeeping, about memory, about how the universe preserves the details of its own story. To understand why this paradox exists, imagine throwing a book into a fire. The pages burn, the ink curls and evaporates. The cover turns to ash. But in principle, the information in the book, the arrangement of molecules, the patterns of ink, the structure of the paper, still exists in the complex motions of smoke, ash, light, and heat. Nothing is lost completely. It simply spreads out in ways that are difficult to reconstruct. For black holes, the question becomes, if something falls in and the event horizon hides it forever, where does the information go? The laws of quantum mechanics insist that the information must persist. Yet for many years, general relativity seemed to say the opposite, that the information is gone forever behind the horizon, inaccessible and erased. Stephen Hawking once argued that information truly disappears inside a black hole. Later, he changed his mind, proposing that the information is encoded in subtle ways in the radiation black holes emit as they evaporate. Other physicists suggested that the information might be stored at the event horizon itself, in a kind of cosmic hologram. This idea, known as the holographic principle, proposes that everything inside a region of space may be encoded on its surface. In this view, the interior of a black hole, with all the complexity of the matter inside, could be encoded in a faint pattern on the horizon. Nothing is lost. Everything is preserved, just written in a form we don't yet know how to read. Some theories go even further. They propose that the quantum structure of space-time at the horizon is not smooth, but subtly textured. Not rough or jagged, but delicately patterned at scales far smaller than atoms. These patterns might store the details of everything that has fallen into the black hole across its entire history. Other ideas explore the possibility that black holes are not purely classical objects at all, but quantum systems with internal states, like atoms with many energy levels. The radiation they emit could depend on these states, carrying faint traces of the black hole's history into the universe. The truth is, we don't yet know the full answer, but the possibilities are beautiful. They suggest that the universe may be far more interconnected and far more careful with its information than we once believed. If you were drifting near a black hole, imagining this gently in the quiet of tonight's story, you wouldn't see anything resembling memory or information storage. You would simply see the dark horizon, perfectly smooth and silent. Yet beneath that silence, physics may be encoding the history of stars, planets, and particles in ways we cannot yet perceive. This idea reframes black holes entirely. Instead of being objects that destroy information, they may be repositories of it, dense, gravitational libraries, storing the quantum details of everything that has ever passed through their horizons. Not in a way people can access, not in a way we can observe, but in a way that preserves consistency in the deepest laws of nature. Physics often advances by confronting paradoxes, and the information paradox has has sparked decades of progress in our understanding of gravity, quantum mechanics, and the structure of space-time. It has inspired new models of the universe that blend the smooth geometry of relativity with the discrete probabilities of quantum theory. The peaceful message behind all this is simple. The universe keeps its memories. Even in places where nothing seems to escape, something remains, encoded, preserved, waiting for a deeper understanding. As we drift into the next part of our journey, we'll explore some of the gentlest and most imaginative ideas about what might lie beyond the event horizon. Wormholes, white holes, and the possibility that space-time itself may be richer and more interconnected than we ever expected. To understand black holes in their full context, it helps to zoom out, far out, until galaxies appear as soft spirals of light and clusters of galaxies stretch across the cosmos like faint lace. From this higher perspective, the universe reveals itself not as a collection of isolated objects, but as a vast, interconnected web shaped by two quiet, enduring forces: gravity and light. Black holes fit naturally into this web. They are not anomalies or disruptions. They are part of the structure, part of the rhythm, part of the way the universe organizes itself across space and time. Imagine drifting through the cosmos from one galaxy to another. Between them lies immense dark space, calm, nearly empty, sprinkled with a few stray stars or thin clouds of gas. But even in this emptiness, gravity connects everything. Galaxies tug on one another softly. Clusters form larger clusters. Filaments of matter stretch for millions of light years, guiding the distribution of galaxies through the cosmic web. Along these filaments, black holes quietly sit at the centers of galaxies, serving as the deepest points in the gravitational landscape. They are the steady centers around which stars orbit, the anchors that stabilize galactic cores, the quiet engines that regulate the flow of gas. But black holes are not the dominant sculptors of the universe. They are participants in a larger cosmic ballet. The true architecture of the cosmos is a collaboration. Gravity gathers matter, shapes galaxies, forms stars, and sculpts the large-scale structure of the universe. Light reveals that structure, carrying information across vast distances, illuminating patterns that gravity creates. Dark matter forms the hidden scaffolding upon which galaxies and clusters grow. Black holes sit at the deepest wells of these structures, quietly influencing motion and evolution. Everything works together, not in chaos, but in a calm, cooperative rhythm. In this vast network, black holes are surprisingly gentle. They don't roam through galaxies looking for matter to consume. They don't dominate space in the way popular images suggest. They remain in place, letting gravity do its work, shaping their surroundings through the smooth curves of space-time. From a distance, a galaxy looks like a glowing whirlpool of stars. Its black hole, if visible at all, would be a tiny dark spot in the center, almost insignificant in size compared to the galaxy around it. Yet its presence helps define the motions of millions of stars, not through force, but through the simple fact that it is the deepest gravitational point in the system. Zoom out even farther, and galaxies themselves become points of light in enormous clusters. Clusters become threads. Threads weave into the cosmic web, and black holes scattered across this web become tiny punctuation marks in a sentence far larger than themselves. The universe is not chaotic. It is structured. It is patient. It evolves slowly, gracefully, through the steady pull of gravity and the soft illumination of starlight. Black holes fit perfectly into this harmony. They are the quiet anchors within galaxies, the places where gravity curves most deeply, the steady hearts in a universe of drifting light. Even the jets and accretion disks we spoke about earlier, those luminous structures that form around some black holes, operate like sparks of activity within a much larger, calmer backdrop. They help redistribute energy. They influence star formation. But they are brief chapters in an enormously long story. From the cosmic web to individual galaxies, from clusters to star systems, from stars to planets, everything is connected by the same fundamental forces. Black holes are one thread in that woven structure, dark, quiet, and elegant. When you think of a black hole, instead of picturing something frightening, you can picture a shape in space-time, a smooth curve, a quiet density, a place where gravity simply becomes deeper than anywhere else. And through that depth, the universe finds a center for its swirling patterns. As we drift toward the final part of tonight's journey, we'll bring all of these ideas together, returning to the beginning, reflecting on the calm nature of black holes, and letting the mind settle into the quiet rhythm of the cosmos. As our journey through black holes draws to a close, we return to the quiet truth beneath all of these ideas, that even the most mysterious and powerful objects in the universe can be understood gently. Black holes are not engines of chaos. They are not cosmic threats. They are simply places where gravity has shaped space-time into its deepest curve. Calm, silent, and steady. Tonight, we drifted through their nature the same way you might drift through a dream. We began with what a black hole truly is. Not a hole, not a void, but a smooth indentation in the fabric of space-time. We imagined what it would feel like to fall toward one, not with fear, but with quiet curiosity. We followed the story of stars collapsing softly, forming the seeds of these dark objects. We explored how light behaves near them, and how the event horizon is not an edge, but a boundary defined by geometry. We saw how time stretches near a black hole, how moments lengthen like the slow inhale and exhale of a deep breath. We reflected on singularities, not as violent points, but as placeholders for the limits of our understanding. We saw black holes grow, not by devouring everything, but by quietly gathering matter over cosmic ages. We watched the elegant jets that form near some of them, and the stillness of the giants at galactic centers. We visited Sagittarius A, the gentle heart of our Milky Way, resting quietly in the darkness. We explored how the Event Horizon Telescope gave us our first glimpses of these objects, stitching together the faint glow around them. We listened to the soft ripples of gravitational waves, born from black hole mergers that unfold like a slow cosmic dance. We imagined primordial black holes, tiny relics of the early universe, drifting silently through space. We considered how black holes help shape galaxies, and how they may even evaporate over unimaginable spans of time. We touched on the profound mystery of information and how black holes may store the universe's memories in ways we don't yet understand. And finally, we let ourselves wander into calm speculation about what lies beyond the event horizon, embracing the fact that some mysteries remain hidden, waiting for future understanding. Black holes may seem like the darkest objects in existence, but when viewed through the lens of quiet science, they become some of the most peaceful. Their silence, their stability, their slow evolution, all of it reflects the deep patience of the cosmos. As you settle into sleep, let these ideas drift through your mind like soft constellations, gravity shaping space, light bending gently, stars orbiting in calm loops, and at the center, quiet objects that reveal far more serenity than the dramatic stories often told about them. There is no rush here, no urgency, no need to grasp every detail, just the comfort of knowing that the universe is vast, stable, and filled with structures that move at a pace far slower than any of our daily worries. Let your thoughts soften, let your breathing settle, and allow the quiet rhythm of the cosmos to guide you toward rest. Thank you for spending this time with Science for Sleep. Good night.